Okay, let's finish worksheet 6. Uh, so number 6, what values of x do the graphs y equals x squared and y equals negative root x have perpendicular tangent lines? And so, now since perpendicular slopes are opposite reciprocals of each other, we can set the derivatives of the first function equal to the opposite reciprocal of the second function's derivative. And so, so our goal is to find where these two graphs have perpendicular tangent lines. So we're going to have to go through rules for perpendicular lines, but not with their slopes, but with their functions' derivatives. So I'm going to name the first function f of x and the second one g of x. So f of x is x squared, and g of x is, I'm going to get rewrite the radical in terms of rational exponents, so negative x to the 1/2. Okay. We find our derivatives. F prime is simply 2x. G prime is simply going through power rule, negative 1/2 x to negative 1/2, which is negative 1 over 2 root x. Okay, so we're going to set the derivative of one with the negative reciprocal of the other. Okay, so the opposite reciprocal for g prime is 2 root x over 1. Okay, so I just chose arbitrarily to take the opposite reciprocal of the second function. Okay, we set 2x equal to 2 root x, square both sides, and we can bring everything over to one side, factor out the 4x, solve for x, and we get x equals 0 and 1. Okay, number 7. A spherical balloon is being inflated at the instant when the rate of increase of the volume of the sphere is 4 times the rate of increase of the radius. Find the radius of the sphere. Okay, we're dealing with volume of the sphere, so v is equal to 4/3 pi r cubed. Okay. It says that we're trying to find the instant when the rate of increase of volume, that's dv dt, is 4 times the rate of increase of the radius. Okay, so 4 times, that's 4 times multiplied by dr dt. Okay, so we're trying to get to this. So this is the relationship between dv dt and dr dt that we're after. Right? All right, so then to get here, though, we need to get the dv dt and dr dt, we need to find the derivative with respect to time. So let's go through and find our derivative. V becomes dv dt. 4/3 pi r cubed becomes 4/3 pi times 3r squared dr dt. Cancel out the 3, so dv dt is 4 pi r squared dr dt. We're trying to find the radius of the sphere at this moment in time. Okay, so we have dr dt, but we can also rewrite dv dt in terms of dr dt, right? Because dv dt is 4 dr dt. So replace dv dt with 4 times dr dt. So we're able to get rid of one variable. So now we can solve for r, because if we divide both sides by dr dt, that will cancel out. And let's go ahead and just divide everything over to the left side to isolate r squared. So the 4's cancel out, the dr dt cancels out, so we're just left with 1 over pi. Okay, so r squared is equal to 1 over pi. So to solve, we can just take the square root of both sides. So r is equal to plus or minus root 1 over pi. But the negative 1 over pi is not going to make sense, since r is going to be a physical size. So only going to be a positive root 1 over pi. All right, number 8, particle motion problem, PVA problem. Particle moves in the vertical line so that its coordinates is given by y of t. Find the velocity and acceleration function. So we go through power rule. V of t is 3t squared minus 12. A of t is 6 times t. Okay. Part B, when is the particle moving upward and when is it moving downward? So we can simply figure out from velocity where the object is motionless, and then from there we can test the signs on either side of the sign line. So first we need to find out when the particle is motionless. We set v of t equal to 0, factor out the 3, and difference of squares, t plus 2 times t minus 2. So we get t is equal to 2 and negative 2. However, it specifies that t is greater than equal to 0, so we got to eliminate negative 2. So 0 is our starting point, and our critical number is at 2. Okay. We can test values in each interval. So plug 1 into velocity, and we'll get positive and negative, so that's a negative. Plug 3, we'll get positive and positive. So we know that particle is moving upward. Positive will represent up, and negative represents down. Moving up from, up from 2 to infinity, and move from 0 to 2. Okay. And bracket on 0, because at 0, the velocity is positive. At 0, the velocity is going to be negative. Okay. Find the displacement of the particle during the first 3 seconds. So displacement is simply the distance from your starting point to your end point, disregarding everything in between. So my position at 0 is 3. My position at 3 is negative 6. That's the first. So my first 3 seconds is starting at 0 and ending at 3. So then the distance between 3 and negative 6 is simply going to be 9. Find the distance that the particle travels in the time interval. So what we do know is that the object is moving down, gets to time t equals 2, and it starts moving up. So there's a change in direction. So we do need to find out the position at 2, so we can add up the distances, since this object is going back and forth between up and down. So at 2, we plug 2 into the position function, and that's going to get us negative 13. So now we just need to find the distance between these two y values, which is 16. Find the distance between negative 13 and negative 6, which is 7. And then we add these two up. So the particle is going to move a total of 23 units over this time interval. Okay, part E, changed the problem a little bit and made this position function that is given. Okay. And then, so part F is asking for you to graph the velocity function based off of position function. So we can create a sine line based off position function. The graph is increasing, hits a maximum at negative 2, decreasing, hits a minimum at 2, increasing again. Okay. So from here, we can graph our velocity function. 2 and 2 are the critical points, x-intercepts. And to the left, we see that negative 2, we see a positive slope, so we're going to have that portion above the x-axis. Between negative 2 and 2, negative slope, so below the x-axis, and then to the right, positive slope above the x-axis. Okay, graph the acceleration function. Acceleration function, we know that there's going to be a point of inflection at 0. Okay, so and that's our critical point. And then to the left, we see that this portion is concave down, and then to the right, concave up. Okay, we can also find that information based off of the velocity function, right? We see that the minimum is at 0. Okay, this portion is decreasing, so this represents concave down. Okay, this portion is increasing, so that represents concave up. Okay, when is the particle speeding up? When is it slowing down? So anytime you're asking about speeding up and slowing down, you're going to have to compare signs between acceleration and velocity. Okay, so we have to look at acceleration function. Acceleration function is 6t. Critical point is at 0. So what that means is we just 0 is also the endpoint as well. So there's no new critical points that we need to test. So it's all going to be the same signs to the right of 0. So just plug any value into acceleration, like 1 or 2, you get a positive value. So acceleration is always going to be positive. Okay, so then create a sine line and plot plus or minus for acceleration and velocity onto the same sine line. So velocity is negative followed by positive. Acceleration is always positive. So then here we can see that there's the same signs from 2 to infinity. So we know in this region that this particle will be speeding up. Okay, same signs. And then opposite signs that indicates that this particle will be slowing down.